Identifying depression rate among age groups through social networks using sentiment analysis, a research-based project. Team members: Fiza Azam, Maha Agro, Hassan Hafiz. This project is supervised by engineer Memuna Sami. Research background: Depression is a leading cause of a disability across globe. According to WHO, approximately 264 million people suffer from depression worldwide. Many of the researchers concluded that it most likely affects women. Depression has sub-disorders which have different symptoms. Some of them are major depression, persistent depression disorder, psychotic depression, postpartum depression, seasonal affective disorder, and bipolar disorder. The study done by Minu Park et al. Found that there is no significant correlation between age and likelihood of depression. Statistics derived by Amy Moran concluded that depression is linked to change in brain chemistry, hormones, genetics, life events, and physical health. The DSM-5 describes a major depressive episode, at least 2 weeks of depressed mood, as well as at least 6 other symptoms, which are persistent sleeping problems, change in weight and appetite, not enough energy, difficulty concentrating and making decisions, psychomotor agitation or retardation, recurrent suicidal thoughts. The degree of depression in a person is typically supervised in the form of questionnaires that vary widely in the length and format. The most common of these are Center of Epidemiologic Studies Depression Scale, Bax Depression Scale, Patient Health Questionnaire, Zung's Self-Rating Depression Scale. Drawbacks of using questionnaires. Results from these tests are usually determined from the patients themselves or by third party, but never from empirical data. Thus, these questionnaires can easily be manipulated. According to National Institute of Mental Health, depression alone costs approximately as much as cancer. An alternate method is use of social media. Social media is also inexpensive and accessible to virtually everyone. Study conducted by G. Coppersmith reveals that people share personal details about their depression online that makes social media as a potential diagnostic tool. Aim of our study: to identify a depressed and non-depressed user on the Twitter platform, to separate selected candidates into 5 different age groups, to acquire tweets of the selected candidates, and application of the 2 machine learning algorithms on the acquired data to identify rate of depression in each age group. Working of the project. Following are the steps which were conducted: social media platform selection, data collection, data cleaning, forming age groups, algorithm selection and implementation, algorithm testing. Social media platform selection. Twitter platform was selected because of the simple format of its tweet, which can contain approximately 120 characters. A tweet can also contain hashtag, a particular person can be referred with an @ symbol, links, images, and a tweet can also be reshared. Overview of data collection. Depression diagnosis tweets were collected. After further screening, among 4,000 users, actual 378 depressed users were identified and the rest of the public tweets were collected. Similarly, control users were identified among 3,200 acquired tweets, which resulted in the selection of 308 candidates whose public tweets were extracted in the next stage. Depression diagnosis tweets collection. For acquiring tweets of a depressed user, we applied similar approach as G. Coppersmith et al. By running 2 queries: I am diagnosed with depression and I was diagnosed with depression. Our dataset at this point contained 400 diagnosis tweets of the users who mentioned their age along with their recent diagnosis, or who mentioned their age along with their previous diagnosis, or whose age was retrieved from their Twitter profiles. Manual work. We further screened and checked 50 latest tweets of the selected candidates. We checked if most of the tweets were in English. Hence, 378 candidates passed for the next stage. Depressed candidates tweets extraction. 3 tables were created in a database. Tables containing past 2 weeks, past 1 month, and last 3,200 tweets from the day when the diagnosis tweet was posted. All of the public tweets of the selected candidates were extracted, concatenated, and stored in the table in such a manner that each user has only one record in each table. All the table had the same structure and had the following columns: username, which acted as a primary key, age of the user, tweets of the user, depressed column, which had hard-coded value 1 to indicate user is depressed, count, which tells the amount of the core tweets of each candidate. Control tweets collection. We ran the query "Today is my birthday." We gathered 3,200 birthday tweets. Afterward, we followed similar approach as Angela Lace et al. We applied a pipeline of words that included depression and its derivative to the last 3,200 tweets of each user retrieved in the first step. If any of the user was found to use any of these words in their tweet, was removed from the dataset. Hence, 495 users were selected at this stage. Afterwards, among 495 users, unique usernames were selected, hence 441 candidates made to the next phase. Then 100 recent tweets of each candidate were checked manually to find out if most of the tweets were in English or not. By doing this, 308 records were selected. Afterwards, we manually checked birthday tweets retrieved in the first step of each selected user and obtained the age of some of users by doing this. To find the age of rest of the user, we followed same technique as Glenn Coppersmith et al. By using lexicon tools from the World Wellbeing Project by University of Pennsylvania. We extracted 100 tweets of each user whose age was unknown. We made sure that extracted tweets did not exceed the limit that a lexicon software can handle. We entered the user tweets in the lexicon tool, and lexicon tool estimated age of each user through analysis of the language used by them. Control candidates tweets extraction. Similar to depression dataset, we created 3 different tables for the control dataset as well. We extracted data of the last 2 weeks, last 1 month, and last 3,200 tweets of the users when the birthday tweet was made. The table contained the following column: username, which acted as a primary key, age of the user, tweets of the user, depressed, which was a hard-coded value 0 to indicate that user is not depressed, and count, which indicated the amount of the tweets of the user. Data cleaning steps. First of all, we accessed the data from the database and stored it into CSV files. Afterwards, we converted emojis to words, and then we removed the emoticons and converted them into words. Next, we removed the URLs. This is the code of all of the data cleaning steps discussed up till now. Next, we removed all of the non-English words and symbols. We removed stop words except first person pronoun. Then we did tokenization and lemmatization. By the research conducted by Angela Lace et al., first-person pronouns were among the high word occurrences in depressed data. Therefore, they were not removed so that they can serve as a feature. Lemmatization is the process of reducing the number of words into a single root word. For example, converting eating to eat and playing to play. Forming age groups. Our dataset contains tweets of 55.2% of depressed users and 44.8% of non-depressed users. We divided depressed users into 5 age groups. Age ranges selected were 12 to 23, 24 to 34, 35 to 45, 46 to 56, 57 to 67. The diagram shows the amount of users each age group contains. Similarly, we divided the non-depressed users into 5 different age groups. Age ranges remained same as before. The code shows how each record was assigned with its respective age group. Algorithm implementation. We opted for bag-of-words embedding approach. Next, we selected support vector machine and random forest algorithms for our study. Lastly, we fed 547 records of our training set to both of the algorithms for training our models. This is what our training set looks like. Bag of words. Machine learning algorithms cannot work with raw text directly. The text must be converted into vectors of numbers. Therefore, we attempted to quantify depression through an analysis of word frequencies with the use of bag of words approach. Bag of words include the following step: collection of data, designing the vocabulary, creating a document vector whose length is similar to that of the number of the vocabulary, scoring words. Support vector machine. Support vector machine is a classification algorithm is used specifically for the binary classification problems. After analyzing the data, the support vector machine effectively creates a hyperplane that best separates the data points into two classes. Random forest. As the name implies, it is essentially a forest of multiple decision trees. Each decision tree outputs a class prediction. The prediction that appears the most is chosen as the final result by the classifier. This is how we implemented bag of word approach for extracting data features. Next, we imported support vector machine and fed a classifier with the data features extracted above and depressed column of our database as the data labels. Similarly, we imported random forest classifier, set n estimators value to 150, and fed our classifier with the data features and data labels for training it. Algorithm testing. Our test data was comprised of 138 records. This is how our test data looked like. Then we first tested our support vector machine classifier using 2 weeks dataset. These are the results we achieved. In the similar manner, we also trained and tested our model on 1 month data and 3200 tweets dataset. These are the results we obtained. This table shows the result of support vector machine algorithm. Support vector machine has produced good values for recall for the non-depressed class and the precision for the depressed class. However, the other values are quite low. Next, we see support vector machine's result for 1 month data. The results are more or less similar to 2 weeks result, but a bit lower. This is an unexplained phenomena, as increasing the data should have produced a better result. Next, we see support vector machine's result for 3200 tweets dataset. The algorithm produced the optimal results with this data. We contrasted accuracy of the depressed records of each dataset for each age group. The 3200 tweets data has resulted in the best accuracy as compared to other datasets. Similar to support vector machine classifier, we tested random forest classifier for 2 weeks data, 1 month data, and 3200 tweets dataset. These are the results we obtained. The random forest does better overall for all values, and its F1 score is higher than SVM. F1 score is the mean of precision and recall. We observed the same effect with the month data for random forest classifier. Precision and recall are both significantly lower. Again, this is yet unexplained and should be further researched. The 3200 tweets data generates the best result for random forest classifier as well. If we contrast accuracy for age groups, here we see that 3200 tweets data classifier has done the best. We finally conclude that SVM generated better precision for depressed class and better recall for non-depressed class. Random forest produced better results for F1 score. Random forest produced the best result overall. Both of the algorithms generated optimal results with the 3200 tweets dataset. Month dataset produced the poorest results. The week dataset performed second best. Technologies. We used Python programming language, Natural Language Toolkit, Twint API for tweets extraction, Pandas for data frames and CSV operations, SQL database, Demoji API for removing emojis, Emoticon API for removing emoticons, scikit-learn for importing classifiers, Google Colab Notebook, and Lexicon tool by the World Wellbeing Project. References. Thank you.